Transmission lines is an important concept in RF engineering because energy, right? You're propagating energy from one point to another. When you do it wirelessly, you're doing it in air as the medium. If it is a wired transmission, then the wire medium is carrying that signal from one point to the other. Let's say even if it's an optic fiber at your home place, it's going to be from the distribution box to your TV or modem. It's going to be that optic fiber cable. So you see that this propagation happens in two. One is wired, another one is wireless. So we call this unbounded or radiation as wireless. That means energy is propagating in free space. You don't need a wire for that. The second kind is bounded or guided, which is wired. So this animation here below kind of nicely describes you what that phenomenon is. This is kind of an array antenna. You're having a 4x4 patch antenna array, 4x4, totally 16 elements. The phenomenon that you see here is the antenna is radiating up above, so it's radiating energy in this direction, and all of it is unbounded. Of course, it might radiate stronger in some directions and weaker in some other directions, but the propagation is happening in an unbounded, open environment. So that is called as radiation. The other kind of radiation is what is called as bounded or guided, like what you see here. When you feed this antenna structure at this point, you need the signal to flow through and reach the antenna elements so that it starts to radiate out, isn't it? So that line that you see here, the microstrip lines that you see here, these are going to spread that energy out and they're going to radiate, reach to each of the antenna element and they're going to radiate. So you don't want any radiation to happen. The power that you feed here has to be faithfully transmitted to every point here so that each antenna element gets 1/16th of the power that you feed here. There are 16 antenna elements. You're feeding all of them equally. So each of them should get 1/16th. Means that this line should not radiate. Yeah? It should not have any losses. It should not radiate. So that is what is called as a transmission line. So all these lines are called transmission lines. And the patch antennas that you see here, these are the guys that are going to radiate into free space. So to carry that wired transmission line in the past for high power, what people used to do is what is called as just like plumbing. Like in your home, you have this water pipe or the drain pipe. It's carrying water, isn't it? Exactly similar to that. You're having hollow metallic pipes. And these can be either rectangular or circular. And you call them wave guides because they guide the wave along. So for example, if you see a rectangular waveguide like this, a cross section like this, you see how the electromagnetic energy propagates through it from one end to the other. It has certain mode characteristics of how the electric and magnetic field modes are. They are TE and TM modes, but here you're going to be looking at what is called as a different kind of transmission line that only supports transverse electromagnetic mode. We will see that what in a moment. It is typically used for high power applications like those would be carrying the RF energy in megawatts. So you can't be using a cable there. The cable will just break down. So you will be using waveguides like this. So it's like really plumbing. You connect one fixture to the other. You're really connecting it tight. Just like water should not leak, here RF energy should not leak. So it's only for high power applications. Optic fibers, which is what you're using in your fiber optic broadband, yeah, from one end to the other. Set-top box to your modem is what you get as a fiber optic cable. Again, energy is being transmitted as light here. Whereas what we're going to be looking at is a special kind of transmission line which supports a mode called as transverse electromagnetic mode. That's a special mode. What it means is that the electromagnetic energy propagates in terms of electric and magnetic fields. These electric and magnetic fields are vectors. And as the energy propagates, the electric and magnetic field are transverse to the plane of propagation. or the direction of propagation. For example, if I have a transmission line, a two-wire line like this, and if I call this is my Z, the transmission line is along the Z direction. As the energy propagates along the Z direction, my transverse plane becomes the XY plane because it's perpendicular. So if this is my transmission line, then this is my perpendicular plane. So if this is along Z, then this is my XY plane. So transverse electromagnetic modes are those modes where the electric and magnetic field are only on the transverse plane. So they don't have any component of that vector in the direction of propagation. They don't have any Z component. They only have X and Y component in this case. And interestingly, your E cross H gives the direction of propagation of the wave. That E cross H here gives you the direction of the power flow, in which direction the power is flowing in. So once you have a transmission line, the power can be either going to the plus Z or minus Z direction. Simplest transmission line that can support TEM mode is two wires. So if you have a circuit that has two terminals there, and you have a certain source that has two plus and minus kind of signal coming out of the source, what do? You just take two wires, connect one from one, plus to plus and minus to minus, right? So you just realized a two-wire transmission line by doing so. That's the simplest transmission line that you can have. But more importantly, you see that in the figure, there is a term called Z0 that is introduced. And that two wires is not simply drawn like two wires like this, but that are made darker for a specific reason, meaning that it is a transmission line. It is not simply a short circuit from one point to the other. So from here to here is not a short circuit. It's a wire that is long enough. So that's why it's pretty thick, and you write it with Z0. It has a certain physical length, maybe L. You connect it to the load resistance RL. The source here has a source resistance RS. So that's how you figuratively represent a transmission line. Later, we are going to be seeing the parameters of the transmission line, which is two important ones, which is the characteristic impedance Z0 that we have here. We call that as the characteristic impedance. It's not impedance, it's characteristic impedance. Yeah, these two words have to go hand in hand when you describe the transmission line. This guy alone and this guy alone, you can tell them as impedance, but when it comes to transmission line, it's characteristic impedance. It is something that describes that transmission line altogether. And the second parameter is the phase velocity, the velocity with which the signal transmits from one end of the transmission line to the other end. How the Z0 and the VP will translate to the circuit parameters, we will have to know by knowing the electric and the magnetic field. Turns out that for the TEM mode, this electric field will translate to a voltage, this magnetic field will translate to a current. You are more comfortable dealing with voltages and currents rather than electric field and magnetic field. So TEM mode gives you that advantage, and that's one reason why analysis of TEM or modes in transmission lines like this two-wire cable becomes a lot more easier. The simplest design is simpler to also understand. Voltage across the 2 points in the two wires, as well as the current at any point, that is, one is having the plus current and the other one is having the minus current. So this kind of two-wire transmission line used to be very popular in the past for TV cables, for TV antennas, yeah, from aerial to the TV box. But these days, nobody uses that. But some military applications still use these kind of two-wire cables. The other kind is a coaxial cable, which you guys are more familiar with. Here you see that this is plus I and minus I. That means the current directions are plus and minus. So you need these two conductors to realize this transmission line.